Hello everyone, this is Giuseppe Maggiore, and today we're going to continue our introduction to TypeScript. In particular, today we're going to talk about generics. Now, before we discuss generics, let me take a step back and let me mention the deep desire we have as developers to reduce repetition of code. Now, repetition of code in general is considered a bit of a dangerous property because it increases the effort needed to maintain a code base. Because now you have two things, or more than two things, that look exactly the same, and then if you want to change the logic behind that code structure, because the code structure is copied in multiple places, now you have to change it in every one of the places. This is tedious, it's boring, it's unpleasant as a developer to do this. But also, the risk that you miss one leading to inconsistencies in your code base is quite high. So the tools for reducing repetition of code in general, in normal code in the domain of values, are functions. So whenever we say that we have a function add that takes two parameters, x and y, both numbers, and returning, okay, let's say that there's a fair bit of logic. We say that if x is greater than y, and then we return x, otherwise if x is smaller than, I don't know, y divided by 2, we return y, and otherwise we return, this is very random code, x plus y divided by 2, okay? So let's say that there's a little bit of logic in our program that requires, performing all these checks. And you call this logic for in different places in your code. So you call add of 3 and 2, you call it inside a for loop, etc. Oh, pardon. Okay, now, let's say that at some point someone comes and says, no, this x smaller than y divided by 2 doesn't really make a lot of sense, so it has to be just x smaller than y. Now, every place in code where we called add has been adjusted in real time without you having to, as a developer, having to think about, okay, where do I have to change all my logic? This is the power of having this sort of abstraction. This principle of abstraction is also centered around the idea of parameters. What are parameters in practice? Well, if let's say that this little program calls add of 3.2 and add of 5.4. Parameters are the same as saying that basically this code here gets copied and pasted in place of a call to, let's say, add 3.2, but then the values 3 and 2 are simply replaced. The principle of substitution is quite important when dealing with abstraction, and then obviously the call to add 3.2 itself. So let's say that we had const res1 is add 3.2. The result would be substituted to the return statements. So we could say result starts at undefined now, and then res1 is x, res1 is y, and then otherwise res1 is, and here we would need an extra little else, x plus y divided by 2. Now res has to be a number, it doesn't need to be undefined, we can simply give it a value. Oh, of course, and it's not a constant. Okay, so that's roughly what's happening, and if here we had res2 is add 5.4, then basically we would do the same. So you see there's this implicit principle of performing a sort of copy and paste, actually, where the parameters between the brackets find their way here in this virtual copy of the code, and the result is also copied out. So you can see that in order to achieve the very same result, I have to do a fair bit of manual interaction with code, which is not exactly the most pleasant thing to do. That's why functions are so useful and so popular. Okay, so we have this principle of instantiation, that we have our function and it gets instantiated in many places, and if we change it, then all the places where it's instantiated automatically change with it. So it's this sort of a teleportation of changes in almost real time. And then we have this idea of substitution, that the parameters are substituted with the arguments in order to generate a special copy of the code in any place where we instantiate the code for us automatically by substituting the arguments for the parameters and the return the return statements to an assignment wherever we wanted to put the variable. So there's these substitutions are taking place, and they are very powerful. Today we're going to look at generics. Now, the idea of generics is that generics are the very same as functions, but at the level of types. Generics are a way to define one type, just like a function, with parameters, just like a function, that you can instantiate in many places, basically creating this copy where the parameters are substituted with the arguments in many places, and also in such a way that if you just change the definition of the type, all the instances will change automatically. So exactly the same, but at the type level. Notice that because generics are essentially functions but at the type level, it means that it might even be possible to perform some computations on these types, and we will explore this in the advanced course. But for now, let's keep it simple. Okay, so the first example we're going to dive into is the simplest generic type I can think of, because generic types are typically used for representing containers or processes like promise. So they're not exactly the domain with the simplest examples. That sucks a little bit. But okay, suppose we want to define a string counter, a string with counter, pardon. Okay, so we say we have the content, which is a string, and we have a counter, which is a number. Okay, and why could we want this? Because let's say that we have a string, but we also want to trace how many times, I don't know, let's say the string is a special API token, and we just want to count how many times it's been changed. For whatever reason, for billing reasons for our customers, we want to bill them depending on how many times they change this thing. Okay, then clearly we will have increment, which takes a string with counter, and returns the new string with counter which has been incremented. So where the counter is equal to source.counter plus 1. And we're using again the spread operator, which makes a copy of the source minus obviously the field counter, which we are overriding. Okay, and we could also say, okay, we also have a decrement. Yes, very good. Cool. Okay, now because this is the logic of building of our application is based around this increment and decrement of the counter, and the payload itself, the content, is the resource that we're counting around, it might happen that at some point, well, there is also something else that is supposed to get a counter. Okay, so I could say we have the content and now it's a number, and also this has increment and decrement functions. Oh crap. Okay, so now so increment for the string, here we have increment with the number. Okay, now this is already getting out of hand with only 2 instances. Fortunately, the code is exactly the same because, well, especially these increment and decrement functions, they have nothing to do whatsoever with the content. The content just gets copied over, and copying over doesn't make a difference. Okay, but suppose that now I want to have a person with counter, and now the person, the content will be a person, so name string, surname string. Okay, there you go. Ooh, yet another copy. Okay, very boring. Okay, but now let's say that our logic changes, and now we want to have a boolean that says true or false if the counter has been incremented at least once. So incremented at least once, it's a boolean, and when we increment, we set the boolean to true. Okay, now bear with me, because now we have to do this 3 times. First is done, second and third are ongoing, and now I hope you can see how easy it would be to make a mistake. Oh, haha, look, there's a mistake. There we go, the mistake has sort of been fixed. Okay. The more copies we have, the easier it is to make mistakes. Moreover, the less each and every copy adds to the logic of our application. Now, these 3 definitions, they are in a sense very irrelevant because they all say exactly the same thing. And you can imagine that if a piece of logic like this one about incrementing is reused in many places within our domain, then the wish to only write it once and maintain it once instead of maintaining times n, where n is the number of contents you might want to have, becomes always stronger. Enter generics. Generics are a way to define this type and these functions as a generic pattern. Let me show you. Let's I like to put all the instances next to each other so that we can look at what is possible, at what is the same, and how to generalize that same object. Constructing code, maybe I should say. Okay, so you can see that basically what we have is a content with counter. The content, this thing, can be anything, but the rest is always the same. Okay, so this can be anything is a type. So this is any type we want, and we can capture this type by stating that the type content with counter is not just a type, but we put these angle brackets. These are really meant as brackets, and here put a parameter, and this parameter is a type. Now, this thing actually works. Can be anything is quite a bad name for a generic type. The noble Java and C++ tradition would use letters like T, U, and V. I'm more of the functional programming Haskell camp. I like to call these things with the letters in the alphabetic order, so you can call it A, but you might also say no, this is supposed to have a reasonable name, so this is the type of content, or maybe just content. Well, why not? This is perhaps a more expressive name. Okay. Now we may still have these types, string with counter, number with counter, person with counter, but we don't need to redefine everything, because we can simply say that this is a content with counter where the content is string. Now, what we are doing is we're invoking this content with counter function. So here, what we're doing is we are invoking this, and we're putting string in the place of the content. So this is what the compiler is doing for us. It's making this copy-paste with substitution, with scope the substitution, because the substitution even respects scope, and it's doing it automatically for us. Now here we see that the content is a number, so content with counter, number, and that's it. And here we have a person with counter, so the content is the person, so the name and surname, and the rest may come with. Okay. Now in practice, you wouldn't necessarily need to give names to these generic instances, but, well, it's up to you. Perhaps for the person with counter, because there is a fair bit of type definition in here that might be relevant, but for the string with counter, number with counter, it might simply be unnecessary, but up to you. Now we have these increment functions. The increment functions are interesting because well, they are also all the same. We can also say that a function, because let's actually rephrase them without these type definitions. The increment string takes a content with counter of string. Increment number takes a content with counter of number. And of course increment person takes the content with counter of person. Maybe it's time, in order to work professionally, to define the person separately. Yes, much better. Okay, so increment person is now processing this content with counter of person. Okay, you can see that these three pieces of code are exactly the same. So we could say no, they are the same, but so increment with counter. Well, it doesn't always take a string because this is the bit that might change. So this might be whatever, and obviously whatever comes in must be the same as whatever comes out. So it has to be the same whatever. It cannot be whatever one and whatever two. Right after the equal sign, we can put the same angle brackets. The angle brackets come before the definition of an entity in code because the type checker runs before the runtime, because the runtime, well, we haven't even run the application yet today. So what we say is that increment with counter, first in the domain of types, expects one parameter, which is the type of whatever we want to use. Then starts the actual code, which will be instantiated with whatever type we put in the whatever type parameter. Obviously whatever is a terrible name, but it's just to really remark the fact that it can be whatever we want because it's a parameter, and like a parameter, well, as long as you put in a type there, everything is going to work. Okay. Now that we have increment with counter, we don't need increment string, number and person because they happen automatically. Let's also define a constructor according to the same logic. Now, in order to construct a content with counter, then I can simply define a function with the same name as the type itself. I call it a constructor, even though it's not a proper object-oriented constructor. We will see it in the next class. But obviously, well, if you have a function that takes as input some parameters and is the preferred way of creating an instance of a type, then I think it's fair to call it a constructor. Now, the constructor will be generic. It takes as input the content because that is as a type parameter. It also takes as input a value of the content type and returns a content with counter of, well, whatever the content was. Now, the content will be the content parameter we got for the function. The counter will be 0, and has it been incremented at least once? Well, not yet, because it has just been created. Now, there are many mentions of the word content here. So let's dive into it, because the scope now also refers to the fact that a symbol or a word in our program might perform a processing in the domain of types or values. Now, content here, you can also see that the highlighting is properly saying, okay, where has this thing been defined? So if I select this, then the property content in the type definition gets highlighted, because that's what we're talking about. This here is the value that we put in that property, and that is the value of the parameter. The parameter has type content. Look, the type content is a type parameter, and it has been defined here. You can also see that the IntelliSense tooltip is stating that this is a type parameter content. Very good. Now we can create such a content with counter. So I could say content with counter 1 is content with counter. The first thing I pass is the type of the content. So I'm calling this function, but first I'm calling it in the domain of types. And I say, okay, I want to give you a number. And then I pass the content. Now it has to be a number. If I try to pass a string, it's going to break. So if I pass a string here, look, because now I stated that content is number, so I get an error which doesn't mention generics at all. Now here, content has already been stated to be a number, so the parameter has to be a number. End of the story. I can put 3 and be done with it. There you go. Then I can have another one, content with counter 2, takes as input a string. Okay, now the number is not allowed, but a string is allowed, and so on. You can also put inline type definitions. So we could have an inline type, and now I have to provide an object with the desired shape. And I even get intelligence because, well, that type is now known. So, well, the system knows that the argument has to have a number and a string. There you go. And obviously the result, the content is a number, then we have the counter, etc. But obviously the counter and the incremented at least once, they don't change, but the content, here you can see it's a string, here you can see it's a number, and here you can see that the content has this structure with number and string inside. Now, so, well, let's say wrap up this first introduction by finishing decrement. Now decrement is going to be exactly the same, but the operation is going to be -1, and we don't set the flag incremented at least once. And there we are, our very first generic type. Let's continue our discussion by diving into some generic types that are built into the language, in particular arrays and tuples. Let's start with the tuples. Tuples and arrays are in a sense very similar. They are syntactically derived from the same patterns in the language. But as a difference, they are both container types. They both are made to contain multiple elements next to each other, with the difference that tuples specify the types of the elements and their position. So with a tuple you specify I want to have a tuple with 4 elements, and I have to be a number, a string, number, number, number. 5 elements. An array, on the other hand, is a dynamic container in the sense that you may store as many elements as you want, but each element must have exactly the same type. So let's start with arrays. The syntax of arrays comes in 2 flavors. The generic syntax, which I personally find more harmonious with the rest of the language, and the throwback to the 80s C++, and then Java and C# style syntax. Now, let's start with this one because it's the one that most people know. Let's say that I want to have a series of numbers. Now, this will be a number array. There you go. And then you put square brackets, and inside, now, the empty square brackets are okay. This means an empty array. But I could also say 1, 2, 3, 4, 5, 6. Okay. Now, this syntax denotes the fact that we have an array of numbers. If you ask me very personally, I would much rather use the generic type syntax, but it's a matter of taste. I will use this in the rest of the lesson and in the rest of the course, because again I just value uniformity, and I find it very clear here what the argument is. In the case of an array of arrays of numbers, then, well, which we need to adjust now, I really don't like the fact that the priority of the operators goes left to right. So I'd rather say an array of number. I find it a little bit more straightforward. So I'm not just being, a purist of the syntax. Well, I think this is just slightly easier to read. But anyway, okay. Arrays are clearly generic. Why? Because the idea of containing a series of elements in sequence, one after each other, and all those elements having the same type, is quite a general purpose idea, and it is applicable to numbers, it's applicable to strings, it's applicable to whatever we want. And notice that if we tried to put a string in here, we would get a compiler error because we are not allowed to put a string where a number is expected. So we get, the usual type error. What can we do with arrays? Now with arrays, what we can do is we can, for example, iterate the values. So for const x of numbers, and then console.log x. Let's see what this little program does. There you go, it just prints the values one after each other. A typical way of going through all the elements of an array uses its length property. So numbers.length denotes the length of an array. I do prefer to call my index variables I because, well, I'm not that young, so I'm used to calling the index, the iteration variable I, and then we can just pick the element, the current element, with the square brackets syntax. So we put the name of the array and we say, give me element number I. Arrays are zero-based because this denotes an offset, a distance from the start of the array. So the array starts, the first element starts at a distance of 0 from the start of the array. The second element starts at a distance of 1 from the start of the array, and so on. So this element is at position 0, position 1, 2, 3, 4, and 5. Especially for beginners, the risk of making so-called off-by-one mistakes in code is quite high. It's actually quite common to make a mistake and to read, to try to read past the end of the array or skipping the first element. So let me show you, and if one were to try to read element 6, now, this is one of the places where arrays don't really help, because numbers of 6 is just a number, because the expression types as a number, but then we get undefined. In other languages, such as C#, which are stricter around the management of arrays, we are going to get an exception, an error, so the program is not going to continue after attempting to read past the end of the array. We could also attempt to read before the beginning of the array, but there you go. Also, this results in a broken program. Okay, now numbers, numbers being an array, also allows to reassign its elements. So we could say that the first element will be reassigned to 10. This is interesting also because, well, first of all, let me run this program, then you can see that, well, now we're printing 10 because the first element has been changed from a value of 1 to a value of 10. But it's also interesting to notice that numbers was declared as constant, meaning that we can't really reassign the numbers as a whole. I can't do this because numbers is a constant, but I can change the individual values inside the numbers array. How come? Because arrays are a reference type, and this actually does deserve a short dive into. Let me show you. Suppose we have a nested array of numbers. So 1, 2, 3, that's the first array. 4, 5, 6, that's the second array. Now, suppose that I were to assign the second value, 4, 5, 6, on top of the first. So numbers of 0 is numbers of 1. Okay. Now, let's go through the outer array. Now let's use a for outer of numbers. So this iterates the outer array, and for inner of outer, because now we iterate the inner array. Okay, let's print inner, and let's for now forget about this little thing. So now we get all the elements, 1, 2, 3, 4, 5, 6. Okay, nothing special. Let's run this again. Ooh, 4, 5, 6, 4, 5, 6. This makes perfect sense, right? Now let me show you what happens though if I take numbers of 0 of 1, which would be this position. So 0, that will be the first subarray, and 1 will be the second element of the first subarray, and I change it. This value was 5, I change it to 50. And let's run this program. Oh, it has changed in 2 different places. Why? Because arrays are reference types. Reference types are not copied when we perform an assignment. So when we are performing this assignment, we are not making a copy of the whole array. We are simply copying a reference to the same array. So when you pass an array to a function, you assign it to a variable, or you pass it around in general, you are not making a copy because arrays are big, and for performance reasons we don't want to make copies of them all the time. So instead we copy a reference, an indication to that very same array in the same area of memory. And if you use this reference in multiple places and you change one, it changes in all the instances where that reference has also been shared, like we have just seen. So a word of caution: be very careful around sharing these mutable references around, and be very aware of what you are trying to achieve. It's also possible to make a copy of the array like this, and then, well, then you see a slightly more natural behavior, at least a behavior that is a little bit more in line with our mathematical and logical intuition. That if you say that A is equal to B, then you change A, you don't expect B to change because they sort of share a quantum relationship that binds them together at the same time, which is something that's quite weird to think about. It's quite unintuitive and very, 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 very easy to get wrong. Okay, so we can read elements, we can assign elements, and that's and we can check the length of an array, and that's kind of all there is to arrays from the perspective of generics. Arrays have many other methods, so we can perform a for each on all the elements, we can push an extra element on top of the array, we can transform an array, concatenate, get all the entries, filter the elements of an array, search, flatten, perform a flat map. There is so much we can do. I would advise at some point take a look at the documentation, take a look at some tutorials, and in general, depending on what you need to know with array or to do with arrays, at some point, learning to find the answer for yourself will be quite invaluable. Suppose now that you have slightly different scenarios that you could solve with arrays, but which can also be solved more cleanly. Suppose we have a usual type person. It's my go-to type whenever I need a basic example. Okay, and this type you don't want to change. You're happy. Then you want to define a function that returns person with I don't know, with next payment due. Okay, so. And this function has to look, let's say, in the database, and has to find out the person with the who has the next payment due. Okay, and the next payment due might be, let's say, a date time or something like this. So we have a data type, and we would like to return the person and the next payment due together. Now, in JavaScript, in TypeScript, there are 2 possibilities. One is to create an inline object. So you would have the person and the next payment due, and that's a date. And then you have to produce some code that will return this object. So well, you know what? I'm going to just use null exclamation mark, which is a wildcard. It's something that should never ever be used in production, but you get. You can let the compiler shut up for a moment, especially if you're discussing, just types. Okay, so this is nice, and it's an elegant, sophisticated solution. Sometimes, when the types of the different values you want to return are not ambiguous and you don't want to be bothered with the creation of such an anonymous type, it is possible to return a tuple. A tuple is very similar to an array because, okay, first of all, let's dive into the wrong solution with arrays. You could say that this object here, which contains both a person and a date, could be simulated in a sense by saying that we have an array that contains either person or date. Well, obviously this is a very unclean solution. Let's say that we were to invoke this function, and notice that null exclamation mark is really a way to just tell the compiler, I know what I'm doing, just shut up with your errors. It's very dangerous. If I run this program, res will fool the type checker. So we're just going to look at the compiler. Okay, so here we have an array of person or date, which means that we might return a person and the second element a date. Yes, and it would work. But when we get the result, what is res0 going to be? Well, res0 is going to be either a person or a date. And what about res1? Well, it's also either a person or a date. And what about res2? Well, it shouldn't be there, but still, Typescript has no way of knowing that res is supposed to contain exactly two elements, the first of which is a person and the second of which is a date. And I've seen a lot of code in my career where someone had written such a direct dependency between the internals of a function, where we know, okay, the first element is a person, the second element is a date, and code outside the function. But if you were to look at code like these three lines that I'm selecting, because the function is somewhere in another module, it's very far away from your site right now, you might be led to wonder, okay, how do I know that res contains exactly two elements and that they contain also first a person and then a date? You cannot. So having types that are not precise enough can be damaging, because maybe the person who wrote this slightly misguided function might at some point decide that in case of error, well, they might return an empty array if there is no person in the database with next payment dues. And then you are sort of screwed, because the rest of the code expects two elements in this array, but all of a sudden the array might also be empty. I've seen this more times than I can count, to be honest. One way to have, let's say, the ease of use of arrays, but a much clearer specification would be to state that what this function returns is rather a tuple. For a tuple, we put square brackets around the type we want to return, the types we want to return, and we separate those types with commas. So square brackets person, comma, date means that this function is going to return an array that always contains two and exactly two elements. The first of which is a person, the second of which is a date. Look what happens. res0 is now a person. res1 is now a date. And what about res2? We get a compiler error stating that the tuple type person date of length 2 has no element at index 2, also -1. Doesn't make any sense. A tuple cannot be indexed with a negative value. Well, the tuple is still an array at heart, so we still have map, we still have length, we still have all these things. And if you were to push, look at this, this is beautiful. If you were to say, okay, you want to push, what can you push? Well, you can push either a person or a date, and let's take a look at what comes out of this. Let's say that we were to add another date. Oh, pardon, yeah, sorry. Well, now we are exposing here the fact that this tuple is the same as the array that we had before. It's an array of either person or date, but it's wrapped in this tuple that makes sure that we fix the number of elements and the type of the elements at given positions. But you could cast this to an array of person or date and it would work. Tuples allow us to therefore easily give more structure to limited arrays and to prevent errors. And you might wonder, okay, but what if a return person with next payment you might actually return nothing? Well, then in this case, the common practice would be to say that we get either a person or a date or undefined. And there are even so-called null object patterns with the so-called option type, which we're going to see in a moment, that make it possible to manage this in a slightly more structured way. And now, res might be undefined, so you see it says res is possibly undefined, so you cannot look up element 0. You have to first check if res is not undefined, and inside the if, the flow type system is going to allow us to read res, because by checking that res is not undefined, here we know inside the if that res is not undefined, and therefore it's the tuple. And there you go. So, and what's the point of type safety in this case again? Because one could say, okay, you know what, but I know what I'm doing. I'm a good developer. Just give me that array solution. I'm going to make it work. Yes, sure. No one is claiming that type safety cannot be made work. Just the risk of errors, especially as your code grows and your assumptions, your hidden assumptions about code remain undocumented, the risk of making a mistake simply grows together with your code base. That's it. Another extremely useful generic type that is provided to us out of the box by Typescript is the so-called promise. Now, the generic types we've seen so far, the container with counter, the array, and the tuple, are containers, all of them. So they contain data. An array in particular is the quintessential container. It's the quintessential box that you can pack full of items, or you can keep it half empty, or you can keep it completely empty. The nature of the array is to contain elements in the same order in which you put them. Generics in general are very commonly associated with containers, but one special kind of container would be the promise, and it belongs to a group of containers of dynamic containers, you could say, that instead of storing data inside of themselves like a box would do, they are capable of computing this data and making it available. Now, let's dive into it. The type of promise, let's call this P0, is generic. So we can say that we have a promise of, well, let's say that we have a server. Oh, let me recover the person data type. It's always useful. Okay, so let's say you have a server with an API that makes it possible to download a person. Now, you can't say that you get the person immediately because, well, the server might be very slow. The server might not respond because you didn't provide the correct credentials, etc. So how do you capture the fact that you expect something to at some point become a person because you ask the server? In most cases it will happen eventually, but not right away, and so the code has also been adjusted to the idea that you have to wait for this result. You do so with a promise. A promise of person is a container that will eventually contain a person. You could imagine that this is a sort of a warp container that has a sort of tunnel to some process that will eventually provide the data that you have in here as a generic argument, that you provided here as the generic argument. We can also work with promises ourselves. Very often we have to define our own promises for example, for testing purposes when simulating a server or mocking an API. Now, the constructor for a promise, it's generic obviously because the type is generic, and it's a higher order function that takes as input the so-called continuations. This kind of concurrent container takes as input usually or is based on the concept of passing a lambda as an argument that will be invoked by the logic when we have the data to continue the process of computation explicitly. So you are given this lambda, the lambda is the next step, and it expects the result. So instead of returning a result, you pass it to this lambda that will continue. And indeed, the constructor of promise takes as input two things. So it takes as input just one argument, the executor, which is a lambda that takes as input two things, resolve and reject. Resolve and reject represent the continuation that has to be called with a person as an argument if the body that represents the logic of this promise has completed successfully, whereas reject is invoked if we want the promise to fail, to terminate because of the same situation as an error. So if we wanted to simulate an API, we could say, okay, if math.random is greater than 0.9, so 9 times out of 10, normal API is more successful than 90%, by the way, then in this case we resolve. And what do we resolve with? Well, we resolve with a new person. So let's copy it from here. There we go. Otherwise, we reject. Okay, very good. So now we have this promise. How do we deal with the promise? Because I can't really do much about this. How do I get to the person that the promise sort of contains? Now, well, there is not a lot we can do with the promise. Promise allows us to specify then, catch, and finally. Then accepts a callback on fulfilled and also another callback on rejected, which I'd rather have in the catch. So here we will get as input the person that the promise has produced in case the promise has been resolved and not rejected. So I can just print it. And in catch, then I can put, well, let's say reject error, wrong credentials. And then in catch, we can actually get that error, so the so-called reason message, and we can simply print that there has been a problem, and this is the problem. Okay, let's run this little script. Okay, error, there has been a problem, wrong credential. Okay, you see, oh, okay, that was a very lucky 10%. Now you see the person, error, person, error, person. Oh, how silly. The 90% is turned, is flipped. Yes, we had an error with 90%. That's a very bad API. Okay, and you can see now we are mostly getting the person, and sometimes we're getting the error. A nice way of simulating a promise, though, or even nicer, is to resolve or reject after a little bit. So enter set timeout. Set timeout allows us to perform a piece of code, which again is passed in a lambda, after a given number of milliseconds. So let's say that we want to simulate an API that is at least 15 milliseconds, that takes at least 15 milliseconds, plus a random value between well, 0 and 1.5 seconds. We could at some point look into the statistical distribution, because right now it's a uniform distribution between 15 milliseconds and let's say 1.5 seconds. So this is uniform is not good. We should have a more skewed distribution around an average, but for now this will be enough. And then we do the same for rejecting. This way we force the people working on our code base to deal with promises that might fail. One of the huge advantages, by the way, of having promises that are mocked, this is an example of a mocked API, because usually you should have to call a server, but if we mock them, we can make them fail more often locally, because if you're running your web server and your browser and your frontend on your own developer machine, then you're not going to encounter many connectivity issues. That's very unlikely. Mocking promises makes it possible for developers to make some events that would be harder to replicate when developing a lot more frequent in order to build better and more robust code. So I'm a big fan of mocking APIs and making sure that the APIs we mock present all scenarios often enough that developers are helped not to forget. So now if we run this, you can see that it takes longer, because now we have to wait for the promise. Now this is an example of concurrent programming, where then is triggered after a while. How long? Well, it could be long, it could be very long, it could be very short, and it could also be never, because if we end up in the reject branch, then the callback, or better yet, the continuation of then, will never be invoked, and the continuation of catch will be invoked in its place. When dealing with functions that manipulate promises, so here at the top level now we're forced to use then and catch. But let's say that we have a function, let's call it f, that manipulates a promise, and now we get as input a promise of a person, and we want to perform other stuff with it, and then let's say return a promise of a string. So let's say get name. Now, of course, the whole thing is complaining. Now, on one hand, we could simply say, okay, promise.then, then we wait for the person, and then we return person.name. And this would work, because p.then returns a promise itself, because that's the only thing it can return. And p.then returns a promise that resolves with whatever this lambda has returned. Because we can't really ever escape promises. If you're inside the domain of a promise, then you have to wait for the result. And it doesn't matter that you want to get the name of the result. Okay, if you want the name, okay, now you don't have to wait for the whole person, you have to wait for the name. But still, waiting for the name means that first you wait for the person, and then this then method will trigger and filter away the surname, because apparently we don't care about it. A very neat trick is that there is the async keyword in Typescript that makes it possible to write code in a slightly different way. So we could say await p, and await p gets us the person as if it were a variable, but in reality we are still returning a promise of string. But thanks to async and await, we can write code in a linear way, and the whole chain of then and catch will look more as if our code were a bit linear. And because generics can obviously be nested, so let's say that we have a double promise. So inside P there is a rather complicated logic that says, okay, wow, this is quite impressive, that says that the person is hidden inside another promise, because you could say, okay, the first call, the first promise authenticates us, and then the nested promise, and then the nested promise after authentication has been successful, gives us the person, and you can see that await is actually capable of smoothing this out. So it's not awaiting is a bit more than then. It's a combination of then and flatten, which is a very sophisticated little thing. And thanks to promises, arrays, and tuples, we now have the ability to use generics to model not only just, let's say, dumb boxes containing data, but we also have gained the capability of modeling, let's say, very smart boxes that contain data through calculation, so that contain data concurrently, not right away, but eventually. Okay, now it's time to dive into a more articulated example of a generic type that we build ourselves. Let's first start by recalling what a linked list looks like. A linked list is a data structure that stores elements one after each other in a linear sequence. It's very similar to an array, but it has a slight advantage with respect to an array, that is adding an element to the top of the list, shifting all the other elements by one step, which is what we also call a stack, because you put an element on top and that becomes the first element in a sense, the most easily accessible, is very computationally quick to perform. Now, in general, a linked list is defined recursively very elegantly through unions, through discriminated unions. There are two sorts of linked lists. One, which is empty. This is the base case. Every linked list ends with one empty list at its tail. If the list is not empty, well, then it's full. What does it mean for a list to be full? It means to have at least one element. So we have this element, which is called the head. Let's say that the element is a number. And then we have the rest of the elements, which is the tail, which is once more a linked list. This is a recursive definition. It's short, and yet it's very powerful because it encodes potentially endlessly many linked lists in practice, because we never have any limitation as to how many elements can be added. Now, usually, when building such a linked list, we also define two constructors. The constructor for the empty linked list, which simply creates an instance of empty, and the constructor for the full linked list. What does the constructor for the full linked list take as parameters? Well, the head and the tail. The head, which in our case is a number, and the tail, which is a linked list, returning furthermore a linked list. Where the head, let's start with the kind, which is full. The head is the head, the tail is the tail. Notice that in Typescript and in JavaScript, when you're assigning a property with the same name to a variable with the same name, you can just omit the repetition head is head and tail is tail. I don't know which one you like most. This is a bit more verbose, but you know, the battle is not won by saving keystrokes. Okay, suppose that in our application now we have multiple kinds of linked lists. So we have this linked list, which contains a list of numbers. But we also need a linked list which contains a list of strings. And later, a linked list which contains a list of people, and so on. So one might be tempted to, okay, you know what, rename this to linked list numbers. Then we could say that this is empty numbers. This is full numbers. This is quite ugly already, but at this point you can perform the very simple copy-paste linked list. Well, you know what? Let's see if we get lucky. Numbers, and we want to replace this with strings. Oh no, it went up in cursor. No, start here. Okay. Let's try again. Strings, 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 strings. Okay, now this sort of worked. And this is string. Okay, now this is a very error-prone technique, as you can see. And it's also very tedious, but you know, now we have the same structure, the linked list of strings. Suppose we wanted to add yet another method or another constructor or another utility function to linked list numbers, well, we would have to also copy it in linked list strings. And obviously this mechanism doesn't really scale, because now if we want to have linked list of people, and now the head here will be our usual type person. Name string, surname string. Okay, so here the head becomes a person. These become empty people. Oh, okay, that's a sad name, empty people. But unfortunately, well, it can happen. Okay, linked list strings, linked list people, and the tail is linked list people. Oh, and this was person. Okay. Alright, so now we have 3, and imagine whenever we want to add something to all of these 3 lists, to keep them aligned with each other, because it makes sense that in our intention as a developer, these are 3 instances of the same data structure. Now we have to change it 3 times. Given how often lists pop up in actual applications, I really could not imagine this way of working to actually be feasible in any way. So how do we fix this? Well, one could imagine that the compiler could just generate this based on an initial template, and the template would be a generic definition which is going to return, compute these types and functions for us, provided the type we want to have in the head. So we could take the first definition as the prototype and then make it a generic. So link the list of element type. Now, obviously the head will get element as type, and the tail will be a linked list of element. Now, the fact that I'm reusing here the same argument element means that whatever parameter was passed here is going to be equal to the type of the element and the type of the tail. The only thing we really care about is that the type of the head and the type of the tail reference the same content type. Then empty. Empty is also generic. In the type of the element, it will return a linked list of element. And the same can be said for full. Full is generic in the element. The head is an element. The tail is a linked list of element. We return a linked list of element, and you can see that we are done. Now, one might even want to see this process of instantiating a type in practice. So let's call a linked list. I say call because, well, instantiating a generic type really calls a type level function. Linked list is a function just in the types domain. I call it and I say, hey, give me the type that linked list produces, returns with argument number. And that's simply linked list of numbers. And empty numbers, well, this is a function, it's a piece of code. How do I get this piece of code? I call the empty function with number. Yeah, and actually, look at this. Look at this. Oh my god, this is so beautiful and sophisticated at the same time. So I'm saying, look, call empty, which is a type level function in its first argument, because this is still happening in the type domain, and this generates a piece of code, which is this code here, where element has been replaced by number. And you can see that empty numbers is a function from unit, from nothing, to linked list of number. And finally, full numbers will be full of number, and look at this again. It takes as input 2 parameters, number and linked list of number, returning a linked list of number. We could do the same, just calling these functions in the domain of types, and we could say, okay, empty strings, that's empty of string. Now in practice, we're not really saving a lot of keystrokes, but you know, you might want to do this maybe as temporary variables or constants in a specific scope where you constantly reinstantiate generic functions with the same arguments. You might even want to do this. So I don't think this is useless. in general, many people do prefer to instantiate generics on the fly when strictly needed. Okay, just to be complete, I will show the last one, linked list of person. Then you know that this also works. Look, this is the linked list where there is no mention of the generic anymore, and this also works on any type, including therefore custom types like person. Very, very elegant. There are not many languages, by the way, where the fact that a generic can be a generic entity, be it a type or a function or a class, can actually be instantiated, especially the functions can be instantiated like this without providing parameters. So I was secretly expecting to have to do this, to have to repeat the parameters. So had this person, tail is linked list people, and to actually have to call it because, and I think up until, well, in most languages you would be required to do this. So this is again my own personal love letter to TypeScript, being an incredibly sophisticated language that embodies the theory of programming and the practice of programming like no other language. Okay, anyway, away with this, and going back to our lesson. Now that we have defined a generic type such as list, we can start defining accompanying utility and manipulation functions. These functions now need to be generic because, well, linked list has been defined as generic, and so the functions must also be generic in order to maintain this higher level of abstraction. Because we can't really, well, we could define a function that only manipulates a linked list of number. Nobody stops us. So just let me show. Just let me show. So suppose we have a function, stupid name, but it takes as input a linked list of number. This is still allowed, but in general, the fact that we have the generic definition means that we can try to think about functions and utilities and machinery that works for any kind of element, and if we manage to do that, we are going to define objects that are very, very useful for our daily programming activities. So generics also enforce cleanliness and general purpose reasoning. Let's start with one such function, perhaps the most trivial of all. Print all. So let's say I want to be able to print all the elements. So print all elements, it takes as input a list of element, returns nothing. Oh, pardon. Yes. Oh, let me use the old JavaScript style 80s syntax. Okay, with function. I will also show the other syntaxes because I think that's quite important to be fluent with all of them. We start by checking the kind. If it's empty, there's nothing to do. Otherwise, well, we don't need the else because there's a return. So TypeScript knows now if we end up on this line, then the kind is going to be full and there's going to be a head and a tail. Then we simply print the head. And we proceed recursively with print all list.tail. Notice that we don't need to specify print all element. Why not? This is a process known as type inference, which TypeScript implements very competently. And the principle of type inference means that sometimes the generic arguments can be guessed, can be inferred by looking at the arguments. Because list.tail is a linked list of element, then yeah, the argument element that we're passing to print all is the same as the one defined by list.tail, which is also the same print all was originally called with. This is actually only useful to respecify the generic arguments so explicitly in limited circumstances where the arguments might not be clear or where they might actually help whoever is programming understand better what's happening. Okay. Now, there are other ways to write these functions. I will mention them because you might encounter them, and stylistically, you know, it's interesting. You might want to define print all as just a constant, or even as a normal variable, in case you might want to transform it and modify it on the fly. So this is interesting, the ability to manipulate the functions in your module as you see fit. And also another way, which I personally find very interesting because it splits types and values in such a way that the types can be used as documentation and are more easily readable, is the following. We start by specifying just the type of this thing, and we say that print all is a function that takes as input a list. Now actually underscore, we don't really care what the name of the parameter here is, a linked list of element. It's generic, of course, and it returns void. And here, look what we can do. Here we can simply remove everything and just put the parameters. Now, the first line after print all is this sort of documentation, because it's just the structure. What is the structure of print all as a function? Here we can focus on the values with full type safety. So now the list is a linked list of element. So this is clear already. This is the same definition. I really like this. I really like this because it really neatly splits the domain of types and structure, which is really a form of machine managed documentation, if you will, from the domain of code and logic, which is more detailed usually. So it really forces us to see that there are two levels we're working on. One is the level of types, and types really are just obligatory structured documentation, and the other is the usual domain of normal code. Okay, now a function like print all is actually the prototype of generic iteration function, which is often called for each. For each frees us from the fact that we are just able to print an element with console.log at every iteration by making it possible to simply perform any operation we want on each element. Now, what does for each take as input? Of course, the list, and it also takes as input a function, I will call it a double underscore, which knows what to do on our element. So it's a function that goes from element to void. Okay, now notice that, okay, all of a sudden we have a mismatch because we have two arguments, and the first argument is not a list anymore. The first argument, let's call it process head or process element. Okay, let's take a look again at the type of process element. It's a function from element to void. Okay, very good. And then we perform the usual iteration with for each. If the list is empty, we return. If we have an element, well, we process it, and then we continue with for each process element first, of course, because we have to pass it around. And again, the type inference is doing its job. If the type inference had gotten stuck, or we really wanted to document this properly, we would have to, oh, it's unhappy. Of course, because this is in the domain of code, so if we want to be able to do this, we have to repeat the generic argument, and we have to merge the two declarations. We are not going to do this though, because type inference gets us fixes this for us anyway. Alright, now print all is very simply, well, it is a generic function. It takes as input a list of element, and the implementation now becomes a one-liner. For each, the first function we get is, here I want to specify that for each operates on an element. The function is simply console.log, and the linked list we pass is going to be the same list L. Now let's construct a list. L1, full of 1, full of 2, full of 3, full of 4, full of 5, terminated by empty. Okay, very good. And now print all L1. Let's run this, and there we go. We have printed all the elements. If we want, we could even make the function here a little bit more explicit. The fact that we are getting an argument e, which is an element, and then we're just passing it to console.log for automatic conversion to string. Or can we call to string here? No, because not everything has a to string. Okay, and still I find this a little bit more elegant, because ultimately, for each expects a function, console.log is a function, so in one argument, so that's it, we're providing the correct parameter. Very pretty. Now, let's make this look a bit nicer, because especially this kind of function declaration I personally find very confusing. So one of the first things I will do whenever I have to work on a code base which contains generics is define the type of function, which is a function that takes as input a and b, so I don't have to, I really don't like these brackets, argument, colon, arrow, etc. So here I would like to simply say, okay, the first argument is a function from element to void. And again, kudos to Typescript for making sure that void would behave like a normal type, instead of any other slightly older programming language where void cannot be used as a generic argument, because that is really a massive annoyance. Okay, then we are also going to make print all even more elegant, because you notice that there's this argument, the linked list, which is taken in by print all, and then sort of, how can I say, sort of pointlessly passed around, Now, you could imagine that in for each the two arguments, first the lambda, that specifies what we do for each element, and the linked list might and often will be specified at different frequencies. Namely, we have less functions that we want to specify as iteration functions or process functions for the element, then we have lists that we want to pass to for each. So let's split these things. Now I am using so-called carrying. What does it mean? It means that for each takes as parameter just one function. Is generic, it takes as parameter one function which processes one element and returns void, and it then returns a new function that takes as parameter the linked list and finally returns void. This means that in order to pass both parameters to for each, now I do have to do it like this. First I call the first stage of the for each function, and then I call the second, and now I've passed all the parameters. What is the side effect of this? The side effect of this, which I find particularly elegant, is that now we don't need this ugly thing, and for each may simply be called with the first stage and not the second. Well, this does introduce a side effect, namely that we have to first instantiate print all. I don't know if there's a more elegant way to do it. I really don't think so. No, that's a bit of a pity. So we might eventually just want to pass the function anyway. Yeah, I really like the possibility of simply saying, okay, oh, but well, actually, yeah, because here we're calling it, so it doesn't really matter. But the possibility of specifying, okay, let me show this by removing the generics. Print all numbers, so we're taking a step back, would be for each of number and then console.log. This I particularly like, the ability to do this, and then print all numbers can be used like this. I love this kind of definition because it's very essential. We don't need to have another parameter of type linked list, which doesn't really convey any sort of useful information, but it's just a placeholder or a proxy parameter that just needs to be passed along, you know. So yeah, I find this to be a very elegant definition, very clean, and there is not a drop of information in our code in the form of variables, parameters, etc. That is not, how can I say, that is not carrying pure information and no garbage whatsoever. The for each function that allows us to iterate over a linked list is just one of many standard iteration functions that we find in most modern generic collection libraries. Let's dive into some more very common iteration functions. This is not only interesting to take a peek, let's say, under the bonnet and find out how these things are actually implemented in the libraries that we use daily, but it's also a fantastic exercise to learn a little bit more about the design and implementation of generic functions. Now, one very common goal when iterating a collection is to transform all of its elements in one way or another. We could use a for each for this, but it is considered a better practice to try and use higher order functions that more accurately reflect the goal we have. There aren't that many things we typically do with collections anyway. Most for each loops over a collection will either, well, for example, print all the items. Okay, fair enough, then we have it already. Transform all the elements, filter some elements, sort. There was a famous analysis performed by, I think, John Carmack, the creator of the Doom video games and one of the best programmers of our generation, on the source code of, I think, Doom 3. On that, please don't quote me on that. I don't remember on which engine, but it was still, you know, a very big and important and practical code base, and he found out that the vast majority, something like 80% of the for loops, were actually some of these fixed known patterns that you could capture with a higher order function. So these things are very useful in practice, and they make code more readable, and they also reduce the surface of errors. So all of this to say, what we're about to do is actually useful. Let's say that we have a list of numbers and we want to increment each number. Okay, how are we going to do this? Well, this can be done quite elegantly through recursion. I will use this little pattern I like a lot. Oh, wait a second. I'm actually going to go back to choose spaces. I've been sucking it up so far, but I actually really prefer to indent with choose spaces. Okay, so increment will take as input a list of numbers and return a list of numbers where all the original values have been incremented by 1. Okay, so we have our... Well, actually, increment is a function from list of number to list of number. Okay, now we have our, let's say, documentation. Oh, pardon. Well, you know what? Yeah, linked list refers too much to the implementation, the fact that it's linked, but a better name could be list. Okay, less details. Then we have the input list. Okay, so now how do we increment? Well, let's check, because if the input list is empty, then I might as well just shortcut the whole thing and return an empty list. Otherwise, we recreate a new list where the head is going to be the same as the head plus 1, and the tail will be the transformation, the incrementing of the input list dot tail. The beauty of recursion is that it allows us to write very, very little, very highly expressive code. But recursion plus higher order functions will get us a lot further with a lot more elegance. Now let's say that we have another function, decrement, where we want to just decrement every element by 1. Now of course incrementing numbers or decrementing numbers is not the most practically useful scenario, but imagine you have a list of people and you want to get all the ages, for example, or all the birthdays, or all the surnames, or all the cities they were born in, etc. So this idea that you have a list of something and you want to turn it into a list of something else is very common, and whether that something else is, in our case, just the same number plus 1 or minus 1, or it's another data type that requires some significant processing, doesn't really matter. But this scenario is very common. Also, notice that we're creating a new list. This is on purpose, because all of these things are just references, all of these data types. And if you just mutate them and you share these things that might change, let's say, under your feet, that can create confusing and dangerous situations. So in general, it's better to create new instances of the things we want to change rather than mutating directly. Okay. Anyway, so what we're going to do is we're now going to generalize this piece of code. These two pieces of code, because as you can see, they are basically the same. So we're going to create another one. We're going to call it transform. And well, what's the thing that's different? Well, the declaration is the same. The input is the same. The check for empty is the same. Everything is the same. The only thing that's different is what do we do to the head. This is the only thing that's properly different. This. So we want to be able to capture the fact that sometimes we want to add one, sometimes we want to subtract one. Every time it's different. Okay, how do we do this? Well, you might have guessed this already. We are going to get as input a function that tells us what do we want to do on the head. So, and I'm going to use the same carrying structure. So instead of adding a parameter, I will simply say that what we have is a function that takes first as input this transformation function that operates from numbers to numbers. Then we take the list as input, then we return the list as output. Okay, so now the next parameter will be this function from number to number, and this is the transformation function. Now, of course, this whole body doesn't work anymore because the input list looks like it's referring to this parameter and not the list, so let's fix this. We have the we could call this operation, or operation on element, or a transform single element, transform element. Even F could be okay. Let's just call it the operation. Okay, and here what do we do? Well, first of all, transform doesn't work anymore because we have to pass the operation and then the input list.tail. Okay, very good. And here, instead of incrementing by 1, which obviously is not the case anymore, we invoke the operation on the head, and there we go. Now, how do we derive increment and decrement back based on transform? Let me Ctrl Z or Command Z back so that we have the implementations of increment and decrement. Hope. Okay, yes, there they are. Okay, so what is increment really? Increment is simply going to specify that the operation performs +1 on whatever value we have. So the type of increment is still going to be the same, but okay, now I get the input list obviously, then I call transform. Here, the function from number to number takes as input a number, the current element, and performs the number +1, and then we pass the input list. But you might realize, hey, this input list is completely unnecessary because, look, well, if we pass the operation to transform, then the next parameter it expects is the list. And this is what we call partial application of a function. It's a very elegant pattern. Then decrement, decrement, well, is simply going to call to transform with an operation that decrements indeed each value by 1. Refined, isn't it? I really like this. Obviously, the type inference here is powerful enough that increment and decrement just become one-liners, and when something is so concise and so clear and so balanced, then there is no need to even have any extra declarations, or perhaps not even any need to give it a name. So many people just would use this directly in line whenever they want to call such a function and not even bother to create an increment or decrement function that does it for us. Okay, what if now I wanted to turn each number into the corresponding string? Because, I don't know, I want to be able to print these values. Okay, now This is a little bit challenging because in order to do this, and obviously I don't want to break increment and decrement, well, this return value, this number here and this number here, they actually have to become generic. Okay, so we are going to get a transformed element because our functions will now be generic in the element they transform. Now, the operation will be a function from number to transformed element. So we're still sticking to number as an input, but the output we don't know about. And then what do we return? We return a function from list of number, because that is still our reference input, into a list of transformed element. Now, notice that, okay, the compiler is not unhappy. Actually, this whole thing works. So the operation is now generic. It goes from a single number to a transformed element. The input list is still a list of number. And then, well, because the operation gives us a transformed element back, then the call to full, look, it's the generic instance, and it's guessed correctly that it's full over a transformed element, and it creates a list of transformed element. Beautiful and elegant, but then, if we want to say numbers to strings, I can pass transform a function that simply converts each number to string, and look at the type of this. It's a function that takes as input a list of number and gives us back a list of string. Let's call it. Let's say that we want to print numbers to strings, and here we pass, let's say, full of 1, full of 2, full of 3, and then empty. And if we run this, we get, oh, well, you can see 1, 2, 3, 1, 2, 3, and they are clearly marked as strings in the console. Very good. Okay. Obviously, the final step will be to also add an original element or input element, so that we're not bound to work only with strings, with numbers, but we can work with whatever to whatever. There is an unpleasant side effect though. You can see the transform now cannot guess anymore what the input was. This is quite annoying. One could say, okay, so we've taken a big step back because now we have to specify everything number to number. Actually, there's a minor compensation as long as we just specify the input parameter, because right now, if transform can go from any input element to any transformed element, yeah, how is Typescript supposed to guess? You could say, well, we're doing -1, so it's supposed to guess that underscore is a number. Yeah, fair enough, and there are languages that are sophisticated enough to do that, but just guessing what underscore is also something where we can simply give a little bit of help. Funnily enough though, we are free to do whatever we want, so here we could say number, but now we are not bound to numbers. We could define a function from well, actually array of number into something else, and simply transform over it. So let's say we have an array of numbers, number arrays to numbers, where we add all the numbers in an array. So I could say, okay, the input is an array of numbers, and here we perform, can I do just sum? No, I cannot. Do I have to perform a reduction? Yes, let's reduce then. Okay, so the callback will take x, y, and add them together, and we start at 0. There you go. And now number arrays to numbers, look what it does. Well, obviously here it will complain, but let's say we have 1, 2, 3, and then here we have 1 and 1, and here we have 1 and 3, and the result will be, lo and behold, well, 1 plus 2 plus 3, that's 6, 1 plus 1, that's 2, 1 plus 3, that is 4. There we go. And so now we have achieved the full freedom and ability to transform any generic list into any other generic list. You might think, oh, okay, we're done, but code in reality does not look like this. And so let's align to what code would look like in practice. Okay, so now we have transform and we have for each. But this is not how these functions would be called, let's say, in in real life. So let's play a little bit with this. The list data type, well, okay, it's either empty or full, that's good, that's the structure. But also, whether or not we are dealing with empty or full, we want to also specify that a list of elements has some, let's say they are methods. You can use object-oriented programming for this, but it's absolutely not necessary, and it's also quite fun and elegant to do it like this. Okay, so we want to have a for each function. Okay, the for each function, well, we know already what the element is, so the for each function is simply going to look like this, and okay, so I'm adding the for each function to the definition of list of elements. Notice that the constructors empty and full are now broken. Why are they broken? Well, guess why. Oh, pardon, sorry, what a mistake. No. This just returns void, because the parameter list of element, that's if you're calling for each on a given list, the parameter is the list you're calling for each on. My apologies. Okay, anyway, so the only thing that is really left to specify is this, is the transformation function. Okay, so now the constructors empty and full, well, they are not really constructing a proper list of elements, because it's probably going to complain that, yeah, for each is missing, because yeah, it's supposed to be there, and here we get the same, saying a property for each is missing in type blah blah blah, because there's only full, head and tail. But now I'm saying the kind is always there, sometimes there's a head and tail, but there's always for each. And here I'm going to put all the utility functions we just want to carry with us. Okay, now we can say that for each is a function. I can put a first parameter, which I call this, which is a list of elements. So this is the function we are calling for each on, and then we have the operation, which is the function from element to void, yes, and then I simply invoke for each of, well, first the operation and then this. Okay, and it's a bit ugly, I know, but yeah, I don't mind ugliness in boilerplate code, to be honest. I can, yeah, okay, maybe it's a better idea to at least split things up. When code becomes too much, you start to lose the benefit of having these elite hacker style one-liners, but okay, that's life. Okay, cool. Now I have for each, so if I wanted to call now this number arrays to numbers is a list, so I can just call for each now. This is kind of cool, and simply say, okay, print me every element. Let's run this, and there you go, 624. Cool, isn't it? Yes, I think so too. Okay, we could also add a transform. Let's add a transform. Very often transform is called map. Now map will be generic. Will be generic in what? Well, not the input element, because the input element we know already. That's the element of the list. This is a generic list. But what we do need here is indeed the function from element into transformed element, and then map will return a list of transformed element. Okay, now the rest of the program is happy. Of course, the bit that's not happy would be the constructors empty and full, because they are failing to provide an implementation for map. So let's do this. I'm going to copy for each, because it's basically going to be the same. Okay, so map. Well, map will be a generic function, takes as input the transformed element. This we still have. It's the list of elements. The function goes from element into transformed element, and what we return? We return transform over the function with this as a parameter. Let's copy this shamelessly, because it's exactly the same. Now, this number arrays to numbers and this whole transform thingy, now it becomes a little bit easier to perform, because here we have our list, and I can say map and just pass the transformation function, and then just for each and print. It's also very handy because all of these functions, map, for each, etc., because they return another list, you can sort of split up your computation in steps, and that's very elegant. Because let's say that now we want to, I don't know, do something else with the results. Now we have a list of now we have a list of numbers. And look, number 2 unknown, and what do we want to do with it? Let's say that now I want to increment the numbers by 1, and there you go. Okay, so now we get 734, 735. And then let's say we want to, I don't know, check if those numbers are even for whatever reason. Okay, so then the number goes into number modulus 2 equal to 0, and now we have a bunch of booleans. They're all false because... Oh, okay, that's quite random. Let's have at least one true, just to see that the results are different. Okay, very good. But the last thing we would like to do, though, is to adopt for each, or for of, as we have it in the world of JavaScript and TypeScript. And for of requires a specific method or property on our object. The symbol.iterator property takes no input and will give us an iterable iterator of element. So what's happening here? This might look a bit weird. It isn't. So this is just a special name. It's the property that will be invoked whenever we put a list inside a for of. And it has to return an iterable iterator. That's something that TypeScript and JavaScript understand. They know how to get a bunch of elements. That's also why this is a generic interface, by calling the methods of this iterable iterator. Let's spend a second on this. Let's say that we have an iterator, which is an iterable iterator of, say, number. Iterator. Oh no, okay, and let's say this is null exclamation mark, just to see what's in it, and let's basically return and next. And next in particular will simply give us an iterator result, which I guess, yeah, there's a value, which is the current value, and there's done, which says whether or not the iterable iterator is finished iterating. Okay, so relatively easy. Quite cool, actually. We can now define an implementation of this function by using the so-called yield operator. This asterisk here denotes that I'm creating such an iterator, but I'm creating it by invoking a special statement which is yield for every element I want to return. Okay, in the case of well, obviously in the case here of the empty list, where there's nothing to do, so it's just an empty body. I don't call yield on anything because there are no elements to yield. In the case of full, well, at least I have one element, the head, so I'm going to yield it immediately, which simply means, okay, so when you iterate, the first thing you iterate is the head. And then, well then, now that I've stated that, where is for of, yes, now that I've stated that a list of elements can be iterated, well, I might as well I might as well iterate over the tail and yield each element of the tail recursively. So now, instead of for each, what I can do is for const x of, and then this whole transform the list, and then console.log x. One of the things I love about for of, combined with this map and there are plenty of other functions that we will explore in the exercises, is that, so when it comes to defining a list here, so let's say that this is our list, you have this pipeline. This is a a very fluent syntax where you simply keep adding new steps of computation, new steps and new steps and new steps. And again, map is just one of these steps, which by the way is obviously also present in exactly which is present in exactly the same shape in arrays, for example. But when you're done with this pipeline of transformation functions one after the other, then you can just iterate. And this iteration is no more and no less than an invocation basically of for each. And if you want it in lambda format, for each is fine, but otherwise you can just do it with a normal for of, and this is going to yield code that is very very simple to read, and it feels very logical. Well, of course, we don't really need to build our own generic container library whenever we need to store a sequence of items one after each other, or we need something a little bit more sophisticated. And indeed, most programming languages have a standard library of collections based on the ideas of generics and containing the same for each map and many more higher order functions that act as great utilities to process the content of our containers. Thanks to the great efforts of the good developers at Facebook, TypeScript has a very good implementation of most common data structures such as lists, stacks, maps, sets, etc. The library is called immutable.js, and it does combine a few important principles of TypeScript programming. First of all, it uses generics, because we want to have as much type safety as possible. It has all the standard higher order functions such as map, filter, reduce, etc. And even more interestingly, it embraces the principle of immutability as a foundation, meaning that you cannot, like in an array, just randomly change the elements of the array. Whenever you create a data structure in immutable.js, the data structure, that instance will remain exactly the same forever. You want to change it, you cannot, but you can create a new instance of that data type that is the transformation that you require. Okay. Now, first of all, just as a quick refresher, in order to have the immutable library, I need to get a dependency to immutable. We don't need to do this manually. You can simply say add, so yarn add immutable, and the right dependency is going to be added for you in your package.json. The result of this is that in node modules we now have an immutable folder, and the immutable folder contains a copy frozen in time for you right now of the current implementation of whichever version is the latest version at the time when you perform the yarn add operation. Okay, after doing this, you are allowed, this may go, to say import, and then whatever we want to import from. And nicely enough, you can see we have also IntelliSense on the modules that we have included in our package.json. What do I want? Well, I want certainly list, I want set, and perhaps I also want love to have a range. Yes, okay. Let's start by creating a range of numbers. Const first 10 numbers. And then I call range and I say, okay, from 0 to 10. There you go. The type of first 10 numbers is indexed of number. So you can see it's immutable.sec, stands for sequence.indexed of number. This is not a list. I can iterate over this. I can say for each x of first 10 numbers. Oops, first 10 numbers. Console.log x. Let's print this. Let's run this. And we get, well, quite unsurprisingly, the first 10 numbers. What's interesting though about this kind of data structure? So what is this indexed data structure? Let's take a look. Okay, so range returns an indexed. What is indexed? Look, the only thing the indexed, oh, pardon, the data type indexed really contains is, well, okay, to JavaScript, gives us an array to JSON, to array, to sequence, concat, so that there's a bunch of things. There's plenty we can do. And this just represents, if we were to scroll down to this implementation, so indexed of number means it's a collection that can be iterated and that can be transformed like any other collection. So we have map, we have count, etc. But what we are not really told without reading the documentation is that an indexed collection might not contain the values you will iterate over. That's very weird. But actually, very much like promises, indexed is a sort of promise. It says, okay, you can iterate over me, I will give you the values you want. But whether or not those values are coming from let's say an array, so they are readily available in memory, or they need to be calculated by transforming another collection or reading from some data source or whatever, we don't know. Indexed allows us to iterate, but does not guarantee that the iteration will not need to perform some computation, which might also be quite heavy. Alright, it is possible to concretize, to force an indexed sequence to concrete memorization by calling, for example, to list, to array, or one of the other functions that are utility functions that are available to us. But we might not always want to do this too soon. Let's say that we have a range 0 to 10, and then we want to perform an operation. Let's say we want to first add 1 to all the elements, then we want to multiply by 2, then we want to filter all the elements that might have accidentally gotten too large, so anything bigger than 18, for example, and then I want to only keep the values which are divisible by 3. There we go. A very meaningless set of operations. Now, what do we get? Oh, just one value. One value which happens to be false. Okay, whatever. What's interesting about this though, that we started with 10 elements, then we are not creating a copy of a sequence of an indexed of number that contains 10 indexed 10 numbers that are all 0 to 10 incremented by 1, and then another copy with 10 more elements, and then we perform a filter, and then we make another copy, and so on. Indexed, being lazy, does not memorize the result of the sequence, but just the recipe of the sequence. So map over an indexed sequence simply stores the fact, okay, we have this indexed and we have this function and we want to map with this function over this sequence, and that's it. It does not execute it right away. When we call toList, we sort of unfold this lazy sequence of operations into an actual list. Reducing copies. Now for 10 elements it doesn't make any difference whatsoever. But for hundreds or maybe even thousands of elements, this might save us from performing lots and lots of computation. So we can add all the map steps, all the filter steps, all the intermediate operations that we might want. It doesn't really matter because we're not really running anything until we call toList. Lists may also obviously be created based on, for example, arrays. So in this case I'm creating a list of numbers from an array of 5 numbers, and there you go, now I can iterate. Okay. In this case, the type inference has correctly guessed this is a list of numbers. Let's say what happens if I add a string. Okay, now what do we get? Now it's correctly guessed, inferred to be a list that contains either strings or numbers. What if I really wanted to make sure? No, this is supposed to be a list of number. Now then we get an error. The error is at the assignment. It's saying, okay, I'm getting a list of string or number, but you're trying to put it in a list of number. Another way to constrain the type of the list would be to simply add the generic to the list of number. Then, yeah, the constructor knows, okay, I can only accept an array of numbers, so this one here would be an intruder. So, you know, generics coupled with type inference are extensively available in the immutable library. There are so many more data structures. We have, but, oh, let's actually, yes, but let's actually take a step back, because I also wanted to show something else. Okay, so I have this list of numbers, and I'm actually going to print it, because this is also interesting to see. So let's print a list of numbers, but let's also print the corresponding range, because I think that's also super interesting. Yes. Okay, so you can see actually that the range here, it only contains start, end, step, and size. So this is literally just the recipe to compute the sequence on demand. Whereas the list you can see, it actually contains the array in the form of the tail. It's quite a complicated data structure, this. Okay, now what happens if I were to map and say, okay, do +1 on each element. Okay, now look what's happened. The sequence, the range, has been turned into a generic sequence. We only know that the size is 5 because, well, mapping over a collection of 5 elements has a guaranteed size of 5, so, you know, at least we can state that the size is known, and then, well, and then that's it. It's only functions because this stores the map over the range and just, again, knows on demand how to calculate the sequence of elements, whereas the list keeps containing all the elements just one after each other. And the funny thing about the range, when compared about the list, is that, okay, suppose this is a very big range, still, the representation in memory is going to be tiny because it's just it's just, well, actually 2 numbers, start and end, that's all. That's what the range needs to store. If we wanted to save the whole array, well, the whole array would require 10,000 numbers memorized, wasting more memory. And the bigger the data structures, the more the wasting memory. Okay, now, there are plenty of data structures in the immutable, in the immutable collection. And 2 of those data structures are the map and the set. Maps, or dictionaries, associate usually one simpler data type, a number or a string, which tends to act as an identifier, with a more complex data type. So, for example, let's say I have a user from a database, and the ID is a GUID, so let's say it's a string, the name is a string, the surname is a string, and the age is just a number. Okay, and then I have my users. And the users are a map of, well, user ID, so string in our case, but this is just a way to say give me the type of the ID property of the user. We will see a lot more of these advanced types later, into user. And we start with map, with an empty map. Okay, isn't there a map.empty? Oh, I could have sworn there was a map.empty property, but anyway, doesn't matter. Okay. This thing is powerful because if we were to change the ID to a number, which is not exactly a great idea, well, then the code would still refer to whatever type we put next to the ID. So that's nice. Okay. Now, how do we add a user? So let's say that we want to create a new user and make sure that this user is added to the users array, to the users map. What I do is I call users dot set, which creates an association between new user dot ID and new user. Mind you, the IDs must be unique. So if we try to set an ID that was already there, we are overwriting the previous one. But remember when I said that all collections in immutable are immutable. Users.set does not reassign, does not change the map. But what we can do is we can reassign the variable. Users.set will return the new map with this new element added. And this is actually quite a fast operation because it's based on trees, and so it doesn't require creating a copy. It just creates a reference to the previous map with a little structure on top of it containing the new user. It's very elegant. And this gives us the new map, which we reassign just to the variable. So it's just a variable that's changing, but the maps that we create, those always stay the same. And now I can add users. I can add a user with ID 1, 2, 3, 4, 5. The name will be Jack. The surname will be Black. And the age will be, I have no idea, 51. And then, okay, let's add another user. ID 5, 6, 7, 8. 9, alignment is important. John, surname White, age 15, and so on. I'm not going to try too much to add too many examples. Okay, now we can ask if users, for example, has a key 1, 2, 3, 4, 5, and we know the answer to be true, and to say if we have a key with 5 choose in one row, and yes, we have 1, 2, 3, 4, 5. We do not have the second one. We can also try to get the value associated with key 1, 2, 3, 4, 5, and notice that get returns a user or undefined, because get sort of performs a has, and so it checks whether or not the value is there. If it's there, it returns it, otherwise we get undefined. There you go. Also perhaps interesting to try to explore the users, and now you can see that, well, there's an array map node with entries, so this is quite a sophisticated data structure. The most important aspect of the map is that it makes it insanely fast to find out whether an element is there already. So the has operation is super fast. We don't have to go through all the elements of the map to see whether or not there's one with the right key. It's done with a very quick selection that navigates super quickly through the keys, which are sorted in a special order for fast retrieval. And the same applies to get. So getting an element that's there in the map is super fast. So maps are not only a useful way to have unique keys, associated with a respective value, but also to have the fastest kind of retrieval that is possible. All right. So just to give you an impression, if we were performing a series of operations on a map and a list, well, the hardware will make all the difference, but you could have differences of 2 or 3 orders of magnitude in performance, where the list is slower. The list might be 100, in some cases even 1,000 times slower than the corresponding operations on a map. So be advised. So maps not only enforce uniqueness, but they also guarantee extreme performance. And the last data structure, but I'm just going to mention this quickly, is the set, which contains unique values. So if you have a set of same numbers, you cannot insert the same number twice. And sets are used to maintain uniqueness over a set of values, like we have learned from classes of mathematics in the lower schools. So this concludes the very long lesson on generics. This is an intermediate to advanced topic. I think it's important to have it here in the introduction, because it will be impossible as a professional practitioner not to come into contact with plenty of generics in the actual practice of programming. So I think this is something you really have to make your own, at least as a user. Building your own generic classes might come later. For some developers it also never really comes, but using generic classes from existing libraries, from the standard library like array, promise, tuple, and properly understanding how to work with them is a vital skill. Generics also make it possible to write and structure code in a very elegant set of patterns, so if it were only for that, it might also be worth it to appreciate just the beauty of our discipline and to learn how to operate with these tools. Thank you so much for being here, thank you so much for following, and until next time.